Question 10 from Paper 1, Section 1 of the 2024 National 5 Physics Examination from the SQA. A toaster is connected to a 230 volt main supply and is switched on. The heating element in the toaster has a power rating of 1.2 kilowatts. The heating element is the wire that actually heats up. A student makes the following statements about the toaster. Statement 1. The heating element transfers 12,000 joules of electrical energy per second. Statement 2. The plug of the toaster should be fitted with a fuse rated at 13 amps. And statement 3. The charge passing through the heating element each second is 230 coulombs. Take each statement one at a time. So statement 1, heating element transfers 12,000 joules of electrical energy per second. If that was the case, you would have the power rating of the toaster to be 12,000 joules per second, and that becomes 12,000 watts, which is going to be equal to 12 kilowatts, which is not what we have in the question. It's 1.2 kilowatts. So statement 1 is wrong, so we mark that wrong like that. The plug of the toaster should be fitted with a fuse rated at 13 amps. Well, it's standard practice if you're over 700 watts of an electrical appliance, you should fit it with a fuse of the value of about 13 amps. So we'll say that one is correct. Statement 3, the charge passing through the heating element each second is 230 coulombs. A bit working out for this one. We know we've got to find the currents because we know that Q is going to equal to IT. So we can find the currents, which we know we can find from the equation P equals VI. So we just rearrange, we get power divided by the voltage is equal to the current. So what is the power divided by the voltage? The power is 1.2 kilowatts, 1.2 times 10 to the power 3 divided by the voltage, which is 230 volts. So we do that in our calculator, we end up with a value of 5.2 amps. 5.2 amps. So we know then that Q equals IT, and we know that's going to be for 1 second, and therefore we'll get 5.2 amps times 1 second. That's going to give us 5.2 coulombs of charge flowing through it each second, which is definitely not 230. So statement 3 is wrong. So it seems we've only got one statement correct here, and that's statement 2, and it's going to be answer B. Question 11 from section 1. A circuit is set up as shown. You can see the circuit here. We have a battery, we have got a resistor with a voltmeter connected across it, another resistor with another voltmeter connected across it, and that's the famous voltage divider circuit or the voltage sharer circuit. And it tells us a few facts. It goes, the reading on the voltmeter V1 is 3.6 volts and the reading on voltmeter V2 is, and we're asked to find that. Now in all these particular circuits there's a technique to do it. There is a formula, but what we should be doing is relying on our knowledge of what's happening in the circuit. We don't know the voltage of the source, so we have to take each resistor in turn and fill in everything we know about that resistor, V, I and R. Fill it in and everything we know about it. And the same with this resistor here, we can put in V, I and R. And we know that since it's going to be a series circuit, the current through the 16 ohm resistor will be exactly the same as the current through the 24 ohm resistor. So we do know that the resistance here is 16 ohms. And we do know the voltage is going to be 3.6 volts, as we're told in the question, 3.6 volts. So we now can find what current I is. So to find what current I is, we know that I is going to equal to V divided by R. And the voltage is going to be 3.6 volts divided by the resistance of 16 ohms. And we do that on our calculator, we end up with a current of 0.225 amps. We'll just keep it like that now to do our calculation. So we now know that the current through here is 0.225 amps, and therefore the current down here is going to be 0.225 amps. And we do know the value of the resistor is going to be 24 ohms. So all we have to do now then is just work out what the voltage is here, and we can do that by doing our Ohm's law equation, V equals IR, and we know the current 0.225, and we know the resistance is 24 ohms. And we do that in my calculator, we end up with a value of 5.4 volts. So the potential difference measured by V2 across this resistor here, 24 ohm resistor, is 5.4 volts, and that's going to give us an answer of D. Question 12 from paper 1 of the National 5 exam from SQA. A circuit is set up as shown. There's a circuit there. You can see we have a battery. We have a ammeter, which is going to measure the current from the battery. We've got this symbol here, which is going to be an LDR because the arrows are pointing into it. So that's going to be an LDR. And then we have this branch here, this parallel branch where the current is forced to split up. And both resistors are the same value, so therefore the current A2 and A3 will be exactly half the value of A1 because the current's just splitting up here. So let's see what's going to happen here. It says the resistance of the LDR increases as the light level decreases. In other words, as it gets dark, the resistance increases. The light level incident on the LDR decreases, so we're going into the dark, which shown in the table describes the effect of this change on the readings on the ammeter. Well, if we have the situation where we've got the LDR going into the dark, the LDR resistance is going to increase. So the LDR resistance is going to increase. Now if that increases, then what we can say is that the current drawn from the battery is going to decrease. Because the bigger resistance from the circuit, the less current taken from the battery. So the current is going to decrease. Now that means that A1 is going to decrease. The ammeter A1 will have a decrease in its reading when it goes into the dark. Okay, it will decrease into the dark. Now, what happens here then? So let's imagine some numbers here. Let's imagine before it goes into the dark, you've got, say here, 2 amps. Okay. And this current is from the battery. It goes through here. 1 amp will go through that branch and 1 amp will go through this branch. Now, if we put the LDR into darkness, the current's going to decrease. So instead of saying 1 amp, let's just say we're going to get, instead of 2 amps, we'll say the current is going down to 1 amp, which means the 1 amp is going to split and give you half an amp up here and half an amp here. So we can see that both A2 and A3 will decrease also. So for our response, we've got the reading on ammeter A1 decreases, which is correct, and the reading on A2 will decrease, and the reading on A3 will decrease as well. So the answer to that question is going to be 12, and it's going to be A. Question 13 from section 1 of the 2024 National 5 Physics exam from the SQA. 3 resistors are connected as shown. The total resistance between X and Y is, and we're given our 5 responses. Now the 3 resistors are connected in parallel. How do we know? Well, if we've got current coming in here, the current is split up 3 ways, and if the current split up 3 ways here, they must be in parallel. Current goes along this direction, and along this direction. So we can say quite happily that we've got parallel resistors here. Now the formula for parallel resistors is quite simple. It's 1 upon RT, the total resistance, is equal to 1 upon the first resistor plus 1 upon the second resistor plus 1 upon the third resistor. So the total resistance 1 upon RT is going to equal to 1 upon 12 plus 1 upon 6 plus 1 upon 4. So we've got to work out what 1 upon RT is, and you can do that in your calculator quite easily. So if I go now to the calculator, bring your calculator up. The calculator is here. We can do the following calculation. We can use the fraction button to begin with. So we're going to put in 1 upon 12, so 1, and it'll be 12. Then move to the side and add on the other one, which is going to be 6, so it's going to be 1, and move it down to 6, and move this along to the other one to add on another fraction, which is going to be 1/4. So 1, move it down to give you 4, and move it up to give it an equal sign, and that equals 1 upon 2. So we now know that 1 upon RT is 1 upon 2 from our calculator. We don't need to do anything else from that, so that equals 1 upon 2, and therefore we can just invert and say that the total resistance, if we flip things over, has got to equal to 2 ohms, and that's just using the calculator method. So the answer to that question has got to be 2 ohms, and it's got to be 13B. Question 14 from section 1 of the National 5 Physics examination from the SQA. A length of wire has a resistance of 8.0 ohms. The current in the wire is 1.5 amps. And we're asked to find the power developed in the wire. Well, we go through our power equations from the relationship sheet, and we come across this one here. It's got power, and it's equal to I squared times R. And that we use this one because we've got the currents, 1.5 amps, and we've got the valve resistance. That's the one we're going to use. So just plug in the numbers. P equals I squared. It's going to be 1.5. Always remember to square it. Multiplied by the resistance, which is going to be 8 ohms. So the power developed in that resistor comes out to be, if I do it with my calculator, 18 watts, 18 joules per second. And that's going to give us an answer of 18 watts, which is going to give you 14C.